Hi. Welcome to this powerful tutorial of One Perceptron to Rule Them All, dedicated to language and vision. This is part of my tutorial on the ICMR 2020 being held virtually. My name is Xavier Giro, and I will provide you an overview of some of the most interesting applications of language and vision that have converged thanks to deep neural networks. So please allow me to share the screen, and you can start with the overview. First, I would acknowledge my wonderful team with whom I have been working on this field of the convergence of language and vision. And during my talk, while I would mostly cover work from other researchers, I would also introduce the contributions that we have made in our team, basically on UPC in Barcelona. So my background is on computer vision, okay? And my interest in the convergence of language and vision somehow started after a talk by Andrew Karpari in CPR 2016 in Las Vegas, in which basically he gave the chip or the ideas that the computer vision community should pay a lot of attention of what the machine translation community was doing, okay? And at that time, there were kind of the early stages of the introduction of deep learning in computer vision. And I think that what he was telling us is that that both communities were starting to use the same tools, and that would drive us to many exciting new applications and synergies between the two communities. So I have structured my talk trying to follow like this dual vision. So my background is in computer vision, so I'll probably be biased towards that, but I'll do my best also to reflect how the people in language can see this convergence of language and visions thanks to deep learning. So I will first cover some works or some applications basically in which we generate new data. That will be this first part. Then another second part in which what we do is we discriminate between data that we kind of already have. That would be like the most classic discriminative task that we normally use in machine learning. And then at the end, I will talk about the venues for representation learning when we have both vision and language. And finally, like some small briefly pointers to control tasks, which I think that they seem to be like the next big steps into this convergence. So let's start with generative models. And actually, I will start from the beginning and where this convergence between vision and language started. And it was basically to generate text. So the basic idea is that we will have some visual information, let's say an image, and we'll encode this information into a representation and then decode it as checks. And there is the text that we will generate. So these were the basics of the first works on image captioning, in which basically the success of convolutional neural networks into encoding images for image classification, it had been seen with AlexNet for predicting checks between classes actually among 1,000 classes on ImageNet. And instead of just let's say mapping the image into 1,000 dimensional vector, one hot encoding output, now what we have is we encode the image, but we extract a sequence of words. So that's we generate language out of the visual representation that is encoded on the CNN. And there were like a couple of or a few works that were published at the same time. So there was this work on Show and Tell, and also this other work from the Berkeley team and actually Andrew Karpari himself. And they were more or less, they were following the same approach. We encode images with convolutional neural networks to the convolutional neural networks, and then that representation we decode it with a recurrent neural networks, which was a technique that had been successfully applied, especially in the machine learning field at that point. Okay, that was the big revolution in language at that point was in translation, and it was the idea of encoders and decoders from a source language into a target language. So the idea here is like, let's replace the encoding of the source language by the encoding of an image and then decode the caption. There was also another work that was quite interesting, actually, like also followed the same trend that machine translation was following. So at that time, after the basic encoder and decoder for machine translation, there were the attention models were introduced. So that basically the idea is that in translation, in language translation, what you would say is like when we generate words at the output, we would like to focus to attend to some of the words at the input. So instead of just encoding the whole sequence into a single vector, we allow that at decoding time, the decoder has access to all the words encoded at the input. And maybe they don't need to be aligned, the words between themselves. And actually, maybe some of the output words between one source language and another one, they are combinations. So it was nice to be able to attend to different of the input words when decoding the target language. So same idea for images here. The idea is that now when we are going to be generating the caption, we will kind of allow or facilitate the decoder to attend, to focus on different parts of the input image. So now what we have the image, we encode it with CNNs, and now at this point, what you see like these heat maps, they represent the different attentions that the decoder decides automatically in order to predict the sequence, to generate the sequence of words that at the end will generate the caption. Okay, so this kind of if we visualize the attention maps at the output, like in some cases, it was possible to see some kind of relation between the decoded words and the attended areas. So this has a lot of discussion if that's a good way for interpretability, but at least what it's for sure true is that the decoder just looks at different parts of the image at different time steps at the output. More recently, and also following the progress that language has had in machine translation, which basically there was a big revolution when a few years ago there was the transformer model that it was on this paper called Attention is All You Need. But basically what it was doing, it was removing the recurrency that had until that point it had been very popular and broad in many language applications, and it just kept like the attention, not at the output, and the input and on the output. So that means that when we are predicting words, now we are aware, can attend to all the words on the input, and as well and all the predictions that we're doing at the output. Okay, and so this scheme, if you apply to images, that brought some gains also for image captioning, and that you see like the first message that Andrew Karpati was saying, like vision people, you should be looking at what machine translation community is doing. It still applies also this year 2020 with this paper from CAPR. So apart from this, maybe the basic task of image caption, there are like many other tasks that show the convergence between language and vision. For example, another one, and also now I'm more like following the trend that vision took in terms of deep learning. So from the vision perspective, the task of image classification was the first one that was addressed. And then after one, probably the next one was object detection. And if we would do image caption, like why not do object captioning? And that's more or less what this work was doing. It was combining an object detector, but then generating captions for each of the detected objects that you can see here. There's a color mapping between one and another. So actually, we had the chance with my PhD student Amaya Salvador to test it on this live demo that these people from Stanford had. She had like for me, and this guy over here had captions like man has short hair, man with short hair, so that's pretty good. For Amaya, a woman wearing a black shirt, and both two men wearing black glasses. Okay, Amaya for sure is a woman, but it's not that bad. Okay, and it's really good for a live demo in 2016. So we like the idea, and actually probably since then we start working on vision and language. And actually, like a few years later, I had this paper made together with people from Facebook, AI in Montreal, in which actually what we're doing is we're generating recipes. So we had an image. Actually, we then go straight from the image to the recipe. Actually, we first predicted the ingredients. So we encode the image, we decode the ingredients, and then with all the ingredients, we decode and the image features all together. That's what we have here. We have a decoder that generates the recipes. And here that you can see, like, this would be an example of one of the recipes that we generated with a title, the ingredients, instructions. So all this structure was kind of learned from the training data set. And I would not say that, so I think we have never cooked any of these recipes, but they kind of look quite realistic for humans, not for expert cooks. So if you're working on this, I think there's still a lot of work to do. Okay, something that I would like to highlight, and I think it's common in all fields of machine learning, but maybe in visual language, it's one of the most relevant ones. Are the challenges that we have in the sense of biases, in data biases in this field. And there's one of these quite impactful paper, which actually they kind of observe that because of the bias that we have in the data sets for captioning, it was tending to predict in some situations like one gender in favor of another. I would say that probably most of the cases it was biased towards predicting male gender. So it's in this photo, you see a person. It's really, you cannot determine if it's a man or it's a woman. But the model by itself, it was biased towards predicting the male gender words. And thanks to their work, they produce a system that kind of tried to actually predict where it was focusing, where it was predicting these words. For example, in this case, it was really was focusing on the dog when predicting this word. And then by kind of seeing where it was focusing and also trying to figure out if where it was focusing, it was possible to predict if it was a woman or a man. It was possible actually to reduce these biases. So here you have kind of the details. And in general, as you will have the slides online, you can always click on these links and get the details. But basically, they were kind of introducing a loss that was trying to predict if it was feasible to identify the gender of the person, and that was trained by occluding the persons in the data set. And this way they managed to have more neutral and less biased captions. Okay, following the trend on computer vision, the next stage for captioning, actually that was also in the early times, it was for video. So the same as you can consider that images are a sequence of, the videos are a sequence of images. We can also encode the visual features of the video and then decode them to predict sequences of words that may caption the activity in a video. Actually, from the machine learning community, so this comes more from the language community, there was a task at that time that caught a lot of attention of trying to have something called multimodal machine translation, in which the task is like given a sentence in one source language. So in English, a brown dog is running after the black dog, to translate it into other languages like in German or in French or any other language, and kind of try to figure out if by providing an image related to the source sentence, there would be an improvement in the output translation. Okay, so I think the results were not very encouraging, but if you are interested, you can look at this task and how the works that were done around it. Actually, in a more general perspective, there was this recent paper from this year, and they were trying to provide like a unified view for the machine translation task, considering both vision, text, and speech and also suggest that you look at it if you are interested on this task. So one specific type of language that it's especially challenging and interesting when combining the textual language and visuals is sign language. Okay, and in sign language there have also been a lot of progress thanks to deep neural networks. So basically there were works that combine the extraction of CNN features together with recurrent neural networks, and then recurrent neural networks with attention. And as you can imagine, like nowadays, the state of the art, it's when doing kind of the same thing, but introducing transformer architecture as a new architecture. So also the same, again, following the same track that machine translation, language machine translation classic has been following. Another task related to this would be like lip reading. There's these works from, I think, Oxford people, a few of them, that were that kind of combine the analysis of video. So here you can see the lips. Maybe you can read what she's saying. I cannot actually. And the idea here is that they have this network that by looking at the lips, having a crop over the lips, it was possible to predict somehow what the person is speaking. So this would be like the architecture that was proposed at that time. As you see, that's commercial neural networks to encode the video frames, and then in this case, GRU so an RNN to predict the words. Later, there was also this work from also Oxford and DeepMind in this case, in which they made it a bit more challenging by trying to do lip reading in the wild. So they also released a data set, and when you see that results are not that bad, so actually I'm not playing the audio, I'm sorry, but you can actually, the task is actually doing quite a good job. So if you look at the model, actually, if you look at the paper, you will see that they, in the architecture, they have the visual features that will be for the lips. They have the decoder here with so this decoder is an LSTM with attention, and also they also feed the model with audio features. But actually, in the results, they provide ablation studies with and without the audio features. And when you feed the audio features, results are much better, of course, because then it's kind of a speech recognition task. And now in that case, it's more like that the visual part is helping the speech recognition, but they also provide results with visual features only. And these results, they are kind of promising, let's say, and it's a good place to start from. Another application that has attracted a lot of works, it's the task of, okay, when I do image captioning, I would like to know which pixels are referred in the caption. That's called the grounding. So it means that if I have this sentence, so I feel like and I predict cat, I would like to know that when the cat corresponds to this cat. Okay, so when I have a captioning, and that's this work. In this particular work, what they were doing is they were detecting the objects. And then as they were generating the caption, they were looking at which of the objects was mostly, let's say, attended or kind of help into the predictions. And you can, by doing that, it's possible kind of to ground the instances, the objects that are mentioned in the generated captions with the pixels that appear in the image. There was also, there have been quite a few works, but what I would like to highlight from this work is in this work, for training the model, they didn't use bounding box annotations or any local annotations. And actually what they were doing is they were, the annotations were like just had the captions at the global scale for the image, and at inference time, it was possible to predict with a heat map. Here you have highlighted with a star the maximum of the heap map. So for each of the words that are predicted, you can look at the maximum. In this case, so a man, it predicts to this sir here. On the word red, it's kind of the attention map that they built. It's centered around the red uniform of this person, and motocross, it's over here, the bike. And this localization, this weak localization of the concepts mentioned in the captionings, it was trained without local annotation. So that's kind of a weak supervision that made it super interesting. Okay, this will be just an overview of some of the tasks that you can have when you are generating text or predicting sequences of text from images. Now let's go the other way around and let's see how can we generate images from text. Okay, so now input is text, output are images or some visuals. So one of the first works to address this task is a work based on GAN. So now, again, we must go back to 2016. It was the beginning of GANs, of generative adversarial networks, that you probably have seen that they are able to generate synthetic data, which looks very realistic. And at that point, there was already some work that was generating images conditioned with the object class. And then, so these authors, what they wonder is like, why don't I encode a description of the object that I want to generate? In this case, they took a data set of bears. And here you see on top the description that they had. So this small bear has pink breast and crowns and black primaries and secondaries. And with this representation, by encoding this description, you can condition the generation of new images. And you can see the result you see below. Maybe they don't look super realistic, but they kind of match more or less the description that I suppose on top. Okay. And as I mentioned earlier, the idea here was to have a generative adversarial network. So we have the description of the object you want to generate. In this case, they also tried with flowers. So this example is on flowers. They encode it, they add some noise. They concatenate noise to the encoding of the language. And then with that, they condition the generation of an image, and they train with the discriminator. Also notice that in the discriminator, it was also important that the discriminator also had access to the language descriptor, so the description of the caption, so that it would be could make a better task into assessing if the generated image, apart from being realistic, if it was matching the description of the object. Okay, because if you don't condition with this here, the discriminator would just tell you if the image is realistic or not. So quality improved some 1 year later, I think, with StackGAN. So that was quite an improvement on the quality of the generated images. So you see that it had like 2 stages, but you should look at the stage below, in which, in this case, the idea of the birds. In this case, the bird description is a small yellow bird with a black crown and a short black pointy beak. Okay, if you look at the images below, I think they really match pretty well with the description, and they look quite realistic. A little bit later, just one evolution of this work is there was this other work called MirrorGAN, in which what they did is, apart from generating the image, they kind of introduced some cycle consistency. So from the image that was generated, the caption description was also generated, and then it was possible to define a loss term also between the input description and the description, or the caption, if you want, that you generate from the synthetic image. So this idea of cycle consistency, I'm pretty sure you have seen it as well in other works. So now it was applied for this task, and it can help, of course, if you are trying to address this problem. Here you have more examples of obtained with MirrorGAN. The row you have at the bottom, these are the ground truth images. So these are real images. The images you obtain over here on MirrorGAN, they are synthetically generated. And when you have on top are the descriptions of the bird. So now let's just read the last one. So this one doesn't look that realistic. It says a skier with a red jacket is going down the side of a mountain. Okay, I don't know, maybe it doesn't look super realistic, but it totally matches the description that it's presented here. Some other works on image generation, what they did is, so they observed that they could help the task of, in this case, of StackGAN. So if I have a sentence, in this case, the image is not that nice as with the birds. But if they introduce an intermediate step, so a tool called SyncGraph, that kind of what it does is it extracts the entity. So given a text, it extracts the semantic entities and the relations by feeding that into the generator, that improve or made the task easier for the visuals generator. So in this case, the results look much more realistic, and especially when composing objects. Also in this idea of generating images by composition, in this other work, in text to scene, what they did is like they given a description of the image you want to generate. There was a kind of a recurrent model in which it was kind of predicting step by step different objects over the image. So you see it's a sequential task, and this prediction, it's conditioning the prediction of another object, and then another object. And once like different patches have been generated, there was a last step that was kind of filling the blanks. Also in terms of video, there was this work that, so it's not directly generating video pixels, but what it's doing is like, let's say, given a description of a sequence, in this case of a cartoon, it were spotting the keywords that were important, and then given a data set of these cartoons, it was retrieving the different parts that were mentioned. For example, Fred is this character, red hat. You can see a red hat over here. Then once the composition, the raw composition is made, then there was a fusion, a later fusion with the right background. And also going back to sign language, because I'm quite interested on this field, there was also the task of generating sign language. Actually, in this case, pixels were not generated. What it was generated was a sequence of poses. So given a sequence of words, that's what you see over here, a sequence of poses, kind of predicting the sign language, was introduced. In this case, like two things to highlight: transformer architecture was used, as in the earlier when I talked about sign language translation, and also there's a SQL consistency. So actually, what they did is they generated the poses, and in order to evaluate if the generated poses were correct, they took the other model they had, because they are the same authors of the sign language translation, and they translated back to the source, and by doing that, they could train the model for pose generation. Okay. Then with this, I'll close this first part of generative models. I'm pretty sure there are like many other charts, but I think that gives you an idea of the possible things that how you can produce new text or new images with the other modality. Let's look now at the what if I'm not actually trying to produce new material, but I'm trying to solve kind of a classification-like task with discriminative models. So now I will first start with this setup in which we have as an input visuals and language, and the discriminative task, it's defined over text. So here the big star task, the first one that kind of followed this approach, was visual question answering. So in this task, we have a question that the question, in order to be answered, ideally, you would need the image, okay? And I say ideally because actually these data sets and tasks has evolved in time, because at the beginning it was seen that there was a lot of bias in the first versions of this task, and the results, quantitative results, they were not representative enough. Okay, I call it discriminative task because most of the systems that have addressed this task at the output, what they have is a predefined set of answers, and then each answer is a class. So let's say they took the training data set, they took the 1,000, 2,000, whatever, 1,000 amount of most frequent answers, and then they address the task as a classification task across all the possible answers. So we addressed this with 2 bachelor students actually at that time. And basically, like, we just, it's not that we propose that, everybody kind of follow the same approach, but yes, now extract visual features, extract language features, and then I somehow combine them. And here, that's the difference between the different solutions that you will see to this problem. It's how the visual and language features are combined, are merged, so that at the end, you will predict the answer to the question. So, for example, in this work, they were doing some, they were extracting some code from the representation from the question, and then they did some hashing over the pixels, and at the end provide the answer. But as you see, the answer is represented as a kind of a softmax task. Okay. At that time, that was one of the state-of-the-art models. I would like also to highlight that this work, it also introduced something called dynamic memory networks for this task. Actually, they were addressing both so non-visual question answering and visual question answering, so text question answering and visual question answering. And apart from the classic CNN and RNN, CNN encoding, the RNN decoding, for this part, for the visual question answering part, they also had some memory that allowed to improve the results. So at that time, some authors thought that in order to address this task of visual question answering, maybe instead of having like large data sets of natural images and trying to collect questions and answer for that, why not trying to narrow down the question and have a data set or actually a render engine? You can think that it's kind of a simulator, right? That would generate images together with questions over that images. And that's that's where the clever data set engine was born. And now you see that all the questions now are like, are there an equal number of large things on metals fields? So these are questions that it's really hard to have a bias in the data set, or at least you can control it. And by doing that, it's easier to measure if there are progress in the visual understanding of the questions and the answers. So they're having many solutions for that. I will not explore all of them. Just as a reference, the same authors, they propose at some point to first try to generate a program. So try to generate some pseudo code that was later executed to do the reasoning. Or there was this other work from DeepMind that what they're doing is they were kind of building representations for each pair of possible objects, and then by considering like each possible pair and the question, they kind of somehow solve the task of classification over the questions, over all the possible answers, basically. Okay, the next, so apart from doing this visual reasoning, that was the next step after visual question answering, like another research direction that came after visual question answering is like, why just limiting to one question, right? Why don't engaging into a dialogue about the image? So here what you have is you have an image, you may have a dialogue history, okay, and then a question. So now it's not just image and question, but you also have a dialogue quiz history. And then if our model now will generate an answer, actually this would this question and this answer could actually go into the dialog history and then even keep extending that dialog a bit farther. And related to this, if you allow me, I will highlight that in ICMR, so the place where I'm presenting this tutorial, we have a demo on one application of visual dialogues in which we have like a proposal to use this technology for treating dementia, because there's something called the reminiscence therapy that is actually, the idea is just to show images to the patients, so patients maybe in the early stages of Alzheimer's, and engaging with them in a conversation, so that brings them back memories. And this task, of course, nowadays it's done, let's say, manually. So there are therapists that speak to the patients and try to evoke these memories. And we think that a nice application of visual dialogues will be this one. And if you're interested, we encourage you to come to the demo session on Wednesday and talk to Mariona Carós, who actually did this work together with our colleagues from the Universitat of Barcelona. Okay, so that's kind of the outline of our system that we had. It was called ElisaBot. What we did is we show an image to our system, and then, we show images from past experiences. Then we show, with all these data set of images that we show to ElisaBot, the bot chooses one of the image and shows it to the patient. Then the patient, there's a question about it, the patient will answer to that question, and then the bot just provides some feedback, some comment about the answer, and then poses another question. Then that is possible to engage into a conversation. We just made a slow scale study, but patients seem to like it, and they found it kind of natural. Also, just to finish on this part of discriminative, also in our group, we had another application that we could call of AI for good, of language and vision. In this case, the idea was to help content providers of social networks to moderate their content, because there's one specific type of content called memes that kind of combine visuals and language. And some of these memes, they are being used to spread hate speech. And it's really hard to detect that automatically, because it's really, it's very multimodal. There's so many hidden ideas, cynicism, or it's really hard, okay? So we set a baseline there, and we actually saw that it's really hard, but if you want to look at it, you can check our paper and code as well. So that would be a first overview of discriminative tasks that you can do when predicting checks. Let's do the other way around. What if now we want to solve discriminative tasks over images? So now what we have as input, you will see that we will have like language and visuals or images, and then some output that it's kind of related to the image. So it has a visual output. So for example, one task would be like, what if I have an image and I want to detect an object, and I want to interact or refer to the object in a natural way. And that's what language allows doing. So for example, here you have a video sequence, and with the query woman with ponytail running, it's possible to actually detect and track the object. That's what this work did. And actually in this work, they kind of show that apart from being that possible, you could actually help, like maybe if you have some tracker that's just tracking objects like woman, and that's it, or objects without any description. If you have a textual description, English description, that would improve an existing tracker. And also they show that their model was managed to handle, let's say, these are not occlusions, it's like that appearance and disappearance of the objects. That's people from Amsterdam. Also, one of the latest works on this idea of what if I have a query and I want for, it's kind of a grounding task somehow. But in this case, what they do is they detect the objects as well. So what they're doing is we are mapping each components of the query into the objects of the scene. And again, the latest version, it's using transformers over the objects and the language. Another work, which it's not on grounding, but it's more like on the object detection and segmentation. Actually, in this work, it's called MatNet. So there's a data set. So what these authors did is they took an existing data set, so COCO, maybe you have heard about it, for vision objects, and they built referring expressions, so linguistic expressions for the objects or many of the objects in the data set. And in that data set, there are like bounding boxes, so you can do object detection, and there are also segmentations. And then they they built a network, and that's the network that they built. So actually, it was composed of 3 different models that were trained separately. One of them, it was mostly focusing on the words, on the subjects. Another one was kind of focusing on spatial relations. Another one on relations between objects. Okay, so they kind of trained that separately, and they obtained very good results for the task of given an expression, generate the bounding box or the segment of the object. Later, there was an extension to video of this same idea. So the same task. Okay, so I have a query that describes an object, but now the object, as there's video, we can. So from one side, it's possible to exploit the temporal consistency. So track the object across video frames, and also now maybe some of the expressions they can refer to motion, which can make it more challenging. In that sense, in our lab, we address this task as well. And we've done different things here. The first thing that we did is we consider video as frame by frame separately and feed it through MatNet. Okay. And then if you have this, let's say this first frame with the image, there's a woman on a horse. Okay, you say the woman on top of the horse, and then MatNet would provide you the mask for the object, or the horse on the water. MatNet could provide you a mask. A dog could provide you a mask. Okay, and now what we did is then we feed that into a video object tracker, video object segmentation engine that we had developed in our lab, which is called RBOS, that actually tracks the objects across the rest of the video sequence. But in this case, it was initialized with a mask that was generated by MatNet based on referring expressions. Actually, have improved the model, and nowadays what we have is a model that is state-of-the-art for different benchmarks for both still image referring expression segmentation and video object segmentation. That's called RefBOS. You can see it you can find it on arXiv, and the source code is there as well. Basically, what we have done is we took like the state-of-the-art model, one of the state-of-the-art models for object segmentation, that is DBLAP3. We took the linguistic representation state-of-the-art from BERT, and we just concatenate them and multiply them, and that's it. And with just one by one convolutions, we managed to obtain very good results. Okay, actually, most of the work it's not on the model; it's more on analysis of data sets, because we observe or we detect is that the existing data sets for these tasks have many limitations. So if you look at the preprint, you will find these limitations and the solutions that we propose for that. Here you have some results of our model. As you can see, if you have I didn't put the language. Okay, yeah, sorry. Here, so that's the input image, and the language query, you have it on top. If it says like man on far left of the screen, you can see it's detecting this man. So there's some mistakes here in this one, because you see there's also some wrong detections over here. But it says like main guy on the TV. In this case, it's detecting the man here on center. Oops, sorry. Or here, if you say woman in blue, it correctly segments that woman. Say guy on right, it correctly segments the cell on the right. So this work was developed by Miriam Melve. And also related to this task, when we addressed that task, as I mentioned, we saw that the existing datasets have many limitations. So in many cases, they were not really addressing the task of referring expressions because maybe the referring expression, the language, was not really discriminating between objects in the scene. Maybe there was only one object in the scene, and then the task was kind of not ill posed. And when we realized that there were a lot of problems in the existing data sets, and we clean it up, then we don't have that much data. So, and as in deep learning, it's important to have a lot of data. What we did is we took an approach that some other people have done in other fields as well, which is like to generate synthetic data. In order to do that, what we exploited is we look at scene graphs. I think I mentioned that earlier in that work that was improving the generation of images. So scene graph, they detect the objects and the relations and also the attributes of the objects. And what we did is we run this out-of-the-shelf scene graph model from the over the video frames, and then as we had the entity name, so the dog, and we also have like attributes, both spatial or bigger or whatever. We kind of built some handcrafted rules to generate many synthetic expressions, like for each object. So it's here, like for the same object, we have like, in this case, like 6 different referring expressions that we can generate automatically and for free with 0 annotation cost. And by doing that, we managed to improve the results that we had obtained. Cool. Then let's address the last big block of this part of the tutorial, which is based on representation learning. So now the goal is not to predict language from vision or vision for language or vision or language, but actually the goal is to learn some representations that will be useful typically for another task. Okay, and let's look at them. So the use of deep neural networks for joint learner representations actually dates back from quite a long time. It received nowadays probably it's the main focus of attention, but it has been looked for quite a long time. So there was this work called Device already in 2013, in which actually what it was done is as given that we have a language model at that point that we were using Skigram language model that you train with a large amount of text, maybe the Wikipedia. I'm not pretty sure what they use here, and we have like another data set that can be trained for image classification. I think they use kind of an ImageNet model or something similar at that point. What is possible, like as in some cases, the label of the image class is also part of the language. We can kind of force that the output of the visual model, it's not just a one-hot encoding of the class that we want to predict, but what we want to do is we can force that the output of the image model, by kind of transforming the representation learned at this point, kind of matches the same representation that it was learned with the language model. Okay, so we just make them kind of match. If we do that, then what is really nice is that, and we train, so this is the same. So with this kind of, we initialize it, so we pre-train this, and now we kind of fine-tune or add some more training into these stages. So now what it's nice is that if there was a word that it was contained in the language model, but it was never labeled on the image data set that we use to train this part, actually now this word, as it's in the language model, we can fit it into the model here, and it will generate some representation. And this representation allows, actually, as representation is the same space as the representation that we also use for image, that would allow to even let's say, retrieve images whose representation is very similar to this object that was never labeled here. Okay, I think I'll go to the next example, otherwise it's too complicated to explain. So that allows what's called zero-shade learning, which basically means that I can detect some classes for which my model has never seen, or in particular, I can detect some objects on my images, even if the model, even if my data set for visual learning does not contain any example of that. So this will be the example. Imagine that we have a manifold of non-classes that are trained with, let's say, ImageNet. Okay, so you have the training images, that's everything you have here, and we built a manifold. Okay, not track, okay, but the ones that are in the manifold. But that in our training images data set, there are no images for cat at all. There's nothing there. But in our language model, we do have the word cat and we have the word track. Okay, so as they are in the language model and we learn a joint embedding, a joint representation for both the language and visual part, what we can do is, like, if we have the word cat, we can really find a representation over here for cat. And if at some point I have an image of a cat, that even if it was never at training time, okay, but if at test time I have an image of the cat, maybe when I feed it through this channel, this image, it's likely that this representation lies close to the linguistic representation, the word representation of the word cat. So, and if now from this point we do like nearest neighbors search to find the right class for this image, it could actually in the end predict that it's a cat. Okay, so the way how this would be kind of predicted, it's like, let's imagine that if we assume that visually cats and dogs, they are kind of similar, and if you don't agree, just think about tigers, okay? But the point is that we have images of dogs in our data set, so we have a way where they are encoded, and also that dogs and cats, when we look at our text data set, so when we look at whatever data set we use here, Wikipedia or whatever, the words dog and cat, they kind of appear in similar contexts. It makes sense that the representations they lie together. So it's possible that if, apart from dogs, you use, there are like other concepts which are related to cats that appear which are visually which appear in similar concept, and they also have like some visual similarities. It's possible that this may work at some point. It's not that it's always going to work, but it's a solution at least. And this allows zero-shade learning. So these are like two different works, but as you can see, they were appeared in the same conference. Another practical application, which maybe it has been more successful, it's multimodal retrieval. So if I have a large data set of images and captions, okay, and I can totally, and they are paired, okay, I can learn a joint representation so that whether when I feed the image or I feed the caption of the image, I project everything into the same position of our multimodal space. And if I do that, later if I have, let's say, if I have an image, a new test image, and I have a large data set of captions, I can retrieve the caption in my data set that best matches my test image, or the other way around. If I have, or the other way around is I have a new caption and I have my large data set of images. So maybe I run my search on a search engine, I describe what I want, and then what I can do is I can encode my description through a language encoder, and then retrieve those images that are most similar to the encoded representation on this multimodal space. And that's kind of an approach that there's a huge amount of literature on this approach. So apart from one of the literature that I will highlight is this work in which they run this multimodal retrieval task with different, so here you have like a query, and now like have it's a kind of synthetic image, I think that it's, and then you have like, you can retrieve real images, clip arts, and more interesting, that's where language is involved. Here it's right special text, is like here it's writes cabinet, door, wall, which is kind of a special distribution of the words, or actually like descriptions, like everything you could need to make dinner, all in one place, not quite the size of a full kitchen. So in this work, what they did is they built a data set of natural images, sketches, clip art, spatial text, and description. So spatial text is this one that I was mentioning. And what they project everything, all the representation. So they learn an encoder for each type of data, and they did the training so that all the representations would converge into the same point at space. And by doing that, you can retrieve one from another. In this idea, and actually also a word from our former PhD candidate, Amaya Salvador, when she was at MIT, she did this task for recipes. So at the beginning, I talked about recipe generation. Actually, chronologically, earlier, what she had done is recipe retrieval. So given an image, she learned some joint embeddings between the images and the ingredients and the cooking instructions. So given an image, you can retrieve an existing recipe instead of generating it. That's a difference with respect to the first example that I provide. So what she did is she just projected the images into the same representation of the ingredients and the cooking instructions. And by doing that, it was possible just maybe you have some recipe and you want to have ideas for presentation of the dish. That's something you could do with this work, this approach. Okay. Then another recent work, also now I'm kind of changing a bit the topic, which is like, what if so this has been a lot of effort lately in really having very good representations that are good pre-trained representations for other downstream tasks. And now I'll just go through some of them. In this case, in this work, what they did is they learned visual representations. Okay, so they wanted very good, rich visual representations. And what they did is, in order to train it, they had like a data set of images and captions of the image. And what they did is they mask some of the word of the caption, and they train a network to predict the missing word. Okay, if you are probably you have heard about this idea, because that's the basics of many language model tasks. So language models, if you are from the vision part, are these let's say neural networks, okay? That what we have trained them by some self-supervised tasks, which means like if I have like a lot of textual data, I come up with some task that I can automatically generate and ask my network to complete. And one of the classic tasks is just remove one part of the data, would be like masking one word and then asking the network to predict it. By doing that, and that's now, maybe I can play the video now. What they were doing is like, so they have child, they mask it, and they learn very good predictions for the representation of the image and the objects. Similarly, at a much larger scale, and then dealing with video, there were like a few works last year on this. This one is called Bilbert, maybe it's one of the most popular ones. And what they did is they took this transformer network that was trained with a language called, then became the BERT model for language, which is one of the most popular models nowadays. And they look at how this language model was trained and kind of adapted it to the case of multimodal, in the sense of if I have like a sequence of video frames and some description, some captioning of that video. So now let's think about that. We have data set of video sequences of video and description of that. For example, in this example, there will be a video sequence. Here you have like 1, 2, 3 frames and a half, let's say. So here there will be a video sequence of a man shopping for something. Then what you see here in between, that would be the neural model, which was a transformer model. And the self-supervised task that they combine, they adapted from the original BERT model. From one hand is what they did is they masked, so they removed some of the, let's say, video frames. Okay, this will be the visual task. So I remove this frame or this frame, and you ask the network to predict the categories that would be detected in that frame. Okay, as you have the whole video, you know the categories, so you can generate your, let's say, your ground truth to compute your loss. But then when you train your network, you remove these frames and you ask the network to predict that. The network will predict that based on the context, basically on the story of the whole video sequence. And that's kind of the idea of BERT, is that these are representations that take into account a lot the context. So if the original idea of BERT is that if you have a word, that word it will not, in many cases, it will not appear in isolation. It's a word in a certain context. So now the same thing is like when you have visual frames, it's interesting that these visual frames, if you want to encode them, if you want to encode these representations, they are also aware of the context. In the way to force the network to look at the context, it's to define self-supervised learning tasks that force the network to look at the context. And one way to force it is just, okay, I totally remove this frame or this other frame, and I ask the network to predict which classes, which semantic classes would appear in this missing frame. So not the pixels of the frame, but the object classes, okay? Because that's much easier to encode and to predict. And also they did the same for the language part. For the language part, that was exactly the same as BERT was doing. So they just masked some of the words. So they masked these two words, but they showed to the model the video sequence and some of the words, and they asked the model to predict, for example, man shopping for whatever. So that was one of the tasks that they use in BERT. Another task that it's also taken from the original language model BERT. So in that, it's an alignment task. So in this case, what they did is they match video sequences with descriptions, with captions. Okay, but at training time, some of them they were matching, some of they weren't, and then they just trained the model. So after the representation you have here, you would have a model that should predict, a network that would predict if they are aligned or not. And of course, you can build as many training pairs as you want for that and learn very high, powerful representations. So with that, they learn nice representations, and they did something similar in this other work. Now, and I'm changing works, but as you see, it's from the same year, and they are similar stories. There's another work called Video BERT, and there were a few others. But for example, if you do that, you can do things like, if I have like a sequence of descriptions of cooking instructions, I can extract the representations that I learned with my whatever video BERT or video BERT, whatever. And then if I have a data set of video sequences for which I have my representations as well, I can retrieve the video sequences, the frames that would match these instructions. So here again, we are not generating video, we are retrieving video sequences to illustrate the different steps of these cooking instructions. Some other works, what they have done is exploiting the correlations between captions and video frames to actually like learn language from video. And in this case, this work from Bristol, from the Acknowledgments team, they learn rich representations to explain adverbs. And in this other work from a Columbia team, and also former students from our group at UPC, they learn kind of the meaning of words that probably you don't know. So if somebody tells you, yes, then I split the GI on the roti, and probably you don't have no idea what it's like. But if you look at the image, right, we can always, many of us, if we didn't know what it was like, we can probably infer that the GI must refer to this sauce, and the roti it must be like what the food that was already in Japan. Okay, so by trying to exploit these two correlations, you can build nice representations for both GI and roti, even if we don't know it. But as we have some pixels there, that can help us. Cool. Let's just address now the last part of this tutorial on language and vision, which would be like what is going on the field of control task. And when I say control, I kind of, maybe some of you have heard about embodied AI. So embodied AI is a field in which you have an agent that is interacting with the environment, and this agent can follow language instructions. For example, they can follow instructions like go to kitchen, which is, what you can see here, it's an example on a platform developed by Facebook called Habitat, or instruction following. So turn around, go out of the bathroom, turn right, and go out of the brown door. So if you have this is a body question answer. What color is the TV? It's dark blue. So which, in order to answer for the questions, you need an agent to take actions. That's why I call it like control task. And there's a lot of interest there. There's this platform Habitat, and there are like a few others out there that are trying to go beyond from what we have seen so far in the previous slides. One of these tasks that is most popular is navigation. So maybe you provide to your agent with some instructions on, for example, go down the stairs, go slide to the left, to the bottom of the bottom, and go through the door, take an immediate left, blah, blah. Okay, and then what you would like is your agent. So at training time, what you will do is you will train a policy, so a neural network that will issue actions. And these actions will, in this case of navigation, would generate a motion of the agent in an environment. And the challenge here is how to be very efficient with the training, because now, so every time you run an agent in a simulator, that's a lot of computation. So so when we deal with training policies for control tasks, reinforcement learning policies, we must be very careful with the efficiency of the samples, because they are kind of very, so the level of supervision of reinforcement learning, it's very sparse, it's very super sparse, and you need to take many actions before getting a reward, whether positive or negative. So here, I think there's kind of a convergence between the reinforcement learning and multimedia community here. I will address this now as well. So for example, if you want to address this navigation task, there was this work from last year, just a general scheme. What you could do is you could take your instructions like walk forward once. So you encode the instruction, and now you can, if you have like, say, an agent that has a video camera on top, even if it's simulated, you feed your pixels on some convolutional neural networks. Maybe in this case, they were just looking at the last 4 frames to have some notion of motion. They concatenated them, went through a fully connected layer, and by combining the instructions with the current observation of the state, they had an LSTM that was predicting the next action to take. So in this one, it was just move or stop. Okay, it was a very easy example, but I think that here you have you can see that the scheme is exactly what we have been showing you for all the other tasks. So I encode the language, I encode vision, and I issue, in this case, now this is an action. Okay, I write here move, but actually it's not just a word. It's an action that will affect the next observation. That's where things change, and that's where we get into the reinforcement learning realm, in which basically the main challenge is that the supervision is is very, very scarce. So normally, so here, this is a very simple example in which we only have like move and stop, but typically in a real case, it will move like dozens of times before reaching somewhere. And if that somewhere it's the place where it's supposed to go, okay, if you start doing random exploration, that you'll never get there. Its chances are super slow. So learning in reinforcement learning, it's much more challenging, especially if you are trying to train models like LSTMs that have a huge amount of parameters. In that sense, okay, there are many works, but for maybe one of that I would like to highlight. So there's this work from Felix Hill from DeepMind. In DeepMind, they are doing so many things. So for example, they learn how to, in a virtual environment, to handle and move objects around, like put a plane on the bed. As you can see, they are training this on virtual environments. But again, like the ingredients is like a CNN for the visuals, LSTM for the language, and then somehow you will predict a policy, so some actions, and that policy will affect the environment, and then this is the classic reinforcement learning loop. So we reached the end of this powerful tutorial on language and vision, and I'll just finish it with kind of the same way how I started. At the beginning, I said that I was inspired into getting into this language and vision field, in part thanks to this talk by Andrew Karpathy saying like we should look at what the machine translation community is doing, and it has. I think it was a very good point, and like 4 years after, we can clearly see a convergence on language and vision, and many people like trying to do multimodal tasks. Actually, if you are in this tutorial, you must be interested in this. So today, I think that we are in a similar situation, but for the control task, for the reinforcement learning community. I think that we as a multimedia community, we should also learn a lot from them, because it's not that far away. It doesn't look that distant to have some agents, some robots that may move around, and we want to interact with them through language, because that's the most natural way for interaction for us. And these agents will want them to see what we see, because that's the same way of sensing our richest sensors that we humans have. So I think that would be a good tip for you if you want to take some home message. So that would be it. Thank you very much for your time. I hope that the tutorial was interesting, and please see you if you are following this in the live session. See you now in the live sessions for the questions and answer. Bye.